Thanks for the introduction. Thank you all guys for showing up at 9 a.m. promptly. Third day of a very busy conference, quite possibly with a hangover. Appreciate it. Thanks to the organizers for entrusting me with a talk in this plenary session. It's an honor. I really love this conference, so it's great to be here. What I want to talk about today is the one thing that excites me the most about additive manufacturing. And that is, in principle, the capability of controlling the structure, the microstructure of the materials that we make by AAM, point by point during the process in 3D throughout the entire build volume. That's what I refer to as playing with Lego. You can basically make metal parts as if they were pieces of a Lego construction set and decide what Lego brick goes where. And here, obviously, a Lego brick is a specific microstructure. And so, following this theme, I have a couple of stories to tell about today. And I'll just be the storyteller. The people who actually wrote these stories are the people that I listed here and that you can see here. These are my PhD student, Shubo Gao, and my two postdocs, Kar Sofinowski and Stravia Takamala. Stravia now is at MPI in Düsseldorf, and she's working on AM, and she'll be joining academia fully as a faculty member quite soon. Shubo is almost done with his PhD, has a lineup, a very nice postdoc in the US. And Kar was a disappointment. He turned to the dark side and joined a company in Belgium. Rumor has it that he's happy and wealthy, so I guess he can be happy outside of academia too. Not that I know anything about it, of course. So off we go with the sort of introduction to my talk. In my group, we like to use additive manufacturing not as much to make parts with complex geometries, or we like to make parts with complex microstructures, specifically parts that combine dissimilar microstructures that we engineer together within the same build. And the rationale for doing that is, of course, that different microstructures have different properties. And so, together with a topology optimized part, we can also have structural components that integrate possibly mutually exclusive properties, or anyway, different properties together. And we became somewhat good at this. We've developed different strategies to control the microstructure. People call that also site-specific microstructure control. The seminal work by Ryan D. Hoffman-Ockridge a few years back was the first one proposing this labeling, so to speak. And as I was saying, we became somewhat good at this. We can control different features of the microstructure polycrystalline solids, like grain orientation distribution. This is stainless steel 316L. We can control the occurrence of different phases in a duplex steel, so we can control the density of FCC and BCC phases, and also somewhat the shape and the distribution of these phases in the volume. And we can also control the grain boundary character distribution to some extent. This is again 316L. And what you can see here are pockets of red microstructure that comes from the high number of coherent grain boundaries that we have in these pockets, because we use EPSD color coding, that those usually are red, and they are embedded into a matrix, a blue matrix that is reached with low angle grain boundaries. And so the two stories that I want to talk about today are actually those two. I'll start off by looking at grain orientation control, and then the second part of the presentation, I'll talk about this grain boundary character distribution control. This is my visual outline. The idea behind this visual outline is that it should convey the idea that it boils down to the melt pool. And so the first part of the talk, I'll show you how important it is to control the shape of the melt pool, which indirectly controls the direction cells or dendrites solidify, and also how to arrange melt pools in the volume so that you can promote epitaxial growth and control grain orientation. In the second part of the talk, I'll focus more on microsegregation, so chemical heterogeneities throughout the melt pool. All right, so I'm not going to give you a tutorial on LPBF. I take that everybody knows about it. Instead, I'm going to use lots of animation here to describe the mechanisms that enable us to get that kind of microstructure control. For completeness, I'm reporting here process parameters. We all know it's absolutely nonsense and useless to show process parameters, because if you try the same thing on a different printer, you might end up, starting over again with a process parameter evaluation, figuring out exactly which combination of process parameters works for you. But nevertheless, here they are. So this is a schematic view of the powder layer. So you're looking at it in cross-section, which means this is the build direction, and X is the direction along which the laser is scanning in and out of the page, right? So as the laser scans into the screen, it forms a liquid melt pool that, as we know, rapidly solidifies following steep thermal gradients. Because of the shape of the melt pool that is, typical conduction mode type of melt pool, these thermal gradient maxima are tilted, right? They are pointing inward. And as a result of that, they promote the nucleation and growth of cells that are tilted as well. And these cells, as we know, in cubic materials such as austenitic stainless steel, prefer to grow with a 100 crystal axis that is parallel to this thermal gradient maxima. Right, so this is the first message here. After a while, everything is consolidated, and because of this, we basically end up with a melt pool that has two sides with two different fiber textures, which means most of these cells have a 100 axis towards plus 45 degree, minus 45 degree with respect to the build direction, but of course they might have a different grain orientation about those two axes, right? All right, laser backs up on itself, now it scans out of the screen. We have exactly the same situation, with the difference that, of course, there's a little bit of overlap between the two melt pools to avoid lack of fusion defects. Which means that some of these cells will actually grow epitaxially from the cells that were pre-existing in the left-hand side melt pool. And that is because epitaxial growth, in general, is energetically more favorable than nucleating a new grain. So it is true that we established a similar texture, a similar fiber texture here. But now, because we changed the direction of the thermal gradient by 90 degrees, minus 45, and now this plus 45, the cells that will epitaxially grow from this melt pool here most likely will be those which will have a 100 axis along plus 45. And so there will be a selection process already within the layer, which then gets enhanced as you deposit a subsequent layer, and so on and so forth. And so eventually you end up with a single crystal. So this is a micrograph of the etched stainless steel 316L that actually shows this alternating directional growth of cells where these melt pools overlap. So this is the schematic of the crystal that you will obtain. This crystal has, as I said, two 100 time directions at plus and minus 45 from the build direction, which results into the crystal having a 110 type of orientation along the build direction. And then they have a 100 axis red along the direction the laser is scanning. So basically what I'm telling you is that if you keep the laser scan direction constant and you stack melt pools together on top of one another, you should be able to build a single crystal, which is what we have here. Although this is arguably not a perfect single crystal, this is a quasi-single crystal because there are some pockets of grains that don't really follow the same grain orientation I mentioned. But on average, if you look at it, along Z, which is the build direction, most of it is green. Green is 111, of course, so that fits our model. Along X, which is the laser scan direction, most of it is red, which is what I showed you before. Okay, so this is a block of stainless steel about 1 by 1 by 1.5 centimeters tall, quasi-single crystal. Great, so if we can make a single crystal, then presumably we can also make a polycrystal, which is what Carr did. So this is a quasi-polycrystal, and he produced this sample by stacking on top of one another blocks of quasi-single crystal, but instead of keeping the laser scan direction constant throughout the entire build, he changed the laser scan direction discretely after 50 layers. So these are 50-layer thick bricks, and this is, of course, the technique that we refer to as layer-wise engineering of grain orientation, which is a bit of a mouthful, but it gives a very nice acronym. All All right, so here, for instance, you can see the 111 Lego brick. He used a scan direction of 55 degrees with respect to the x-axis that is coming out of the page. And then on top of it, he built a 110 Lego brick, and then a 100 Lego brick by, varying the laser scan direction. You can actually look at this EBSD measurements, EBSD pole figures to convince yourself that the main zone axis are parallel to x, aside from the nice color contrast. Very good. So we can make polycrystals. Now, if you were a PI like me, or a postdoc like Art, or a PhD student, and you would be given a the possibility of making a polycrystal, what would you make? What sort of polycrystal would you create? Well, I mean, lots of people would just, for instance, write the acronym that stands for the university name, for instance, or the funding agency. We've seen a bit of that already over the past 2 days. But we decided to do something else. We decided to prepare or actually make a QR code. So this QR code is effectively uses texture as the fundamental unit of information. So we've encoded information in a chunk of metal, of stainless steel, by using Lego, so by varying the laser scan direction discretely, and created something that can actually be read by a mobile phone. Now, hold on. Usually, what I do at this point is I say, okay, take out your phones and try to scan it, and you'll be redirected to my group website. The truth is that since I left NTU, my online presence has been erased completely. So you will be redirected to a 404 error message if you scan this QR code now, which is a bit sad. I'm laughing, but it's a bit sad. Anyhow, on a jollier aspect or note, the other thing that I wanted to point out about this QR code is that it's a relatively big chunk of metal. If you look at the scale bar here, you realize we're dealing with something like 5 by 5 centimeters roughly, right? So it's absolutely impossible to characterize the grain orientation distribution by EBSD. It wouldn't even fit into an SCM, right? But we do need orientation contrast if we want to be able to read out information of this QR code. So what we use here is a technique that we call directional reflectance microscopy, which we have developed in my lab. And it's entirely based on optical microscopy, but it provides EBSD-like information on large area and very fast. So I don't have time to talk about DRM today, but I just wanted to tell you if you're interested in that, come see me, talk to me during the break, or go to my website, not this one, the new one. Now, both this QR code and the examples I showed you before basically demonstrate the possibility of changing grain orientation discretely in little blocks or bricks, either within the same layer or across different layers. But nothing prevents us from changing orientation continuously through the build and create microstructures that do not exist in nature. This is a helicoidal microstructure. So if you look at the schematics here, or more precisely, if you look at this animated GIF that is basically plotting orientation along the z-axis, you realize that this is a helix grain. So this is a quasi-single crystal grain that keeps rotating as you move along the z-axis. Okay? And the way Carr made this helicoidal microstructure was to vary the laser scan direction each layer by only 1 degree. Now, this is a processing talk. I'm not going to talk much about, actually at all, about mechanical properties. I'll explain why later on. But we're investigating the mechanical response of this kind of microstructure, and it's actually very interesting. But aside from mechanical response, I think that these kind of microstructures could be instrumental to understand a little bit better what are the solidification processes that are at play during additive manufacturing. I mean, even if we don't want to, we often see large intragranular rotations which were not programmed, so to speak, or not planned, in many different samples that we produce by AAM. And so these synthetic microstructures could shed some light into the processing, the mechanisms that control this intragranular grain rotation, because here we can control them. All right. We can also make complex shape microstructures. These are not parts with complex shape. These are microstructures with complex shape. So specifically, we can make parts that combine Lego bricks with curved surfaces or with different geometries in general. These are two different samples with a Lego brick, an island grain with one orientation embedded in a cuboid with a different orientation. We've also made or used Lego with other materials. I showed you stainless steel so far. This is very new work that my postdoc Australia published just recently. You see Lego in a cubic titanium alloy. This is beta titanium niobium. And the mechanisms controlling grain orientation here are exactly the same as the ones that I showed you before. But interestingly, in this paper, in this work, you'll see that she also managed to get a different texture by playing, again, with process parameters, which I report here. And this texture we call a PD texture. PD stands for perpendicular direction because it's perpendicular to the build direction and the laser scan direction. And as you can see from the pole figure here, you have a very strong texture along Y, right? So that's exactly what you see here. And I'm only bringing this up because I think it reinforces the idea that if you want to control grain orientation or texture in general, you can manipulate the melt pool geometries. In this case, we're actually drilling very deep keyhole melt pools. And because of the large depth of these melt pools, the thermal gradients are nearly perpendicular to the build direction. So the cells or dendrites are growing within the layer. And once everything is solid, you'll have the same fiber texture I mentioned before, but this time is, as I said, along the perpendicular direction. Now we still stack these melt pools together. We call this keyhole nesting. And it reminds me a lot about stacks of IKEA glasses, basically. And by doing that, actually, we promote this grain selection process I mentioned before in the area, well, in the two regions, on the two sides, of the melt pool. So if you were to zoom in where this melt pools intersect many times, you'll see that these cells get remelted a lot of times because of this deep nesting. And that's what's promoting, basically, the grain selection process, but in a much more confined volume. All right, I think it's time to switch to the second part of my presentation. And here, I'll be talking about microsegregation, how we can use microsegregation, control microsegregation during LPBF to basically engineer the thermal stability of alloys. This is again stainless steel. And the figure you're looking at here is again an EBSD map, but showing only grain boundary character distribution, is basically a chunk of metal that consists of two different microstructures that are alternating along the build direction. I apologize, I forgot to put here the axis, but this is the build direction. So these two microstructures are the red microstructure, which is a fully recrystallized microstructure containing a lot of coherent twin boundaries, because this is, again, oscillating stainless steel with relatively low stepping fault energy. No texture, or very weak texture, and aqueous grains. This is a blue microstructure. This is a basically as-built microstructure with strong texture and clearly still residual high GMT density and columnar grains. Okay, so the interesting aspect of this is that we can site-specifically change quite drastically the type of property, the set of properties that stainless steel might have depending on the microstructure. And we're really interested in understanding how this responds, mechanical behavior, but also other type of properties. So this was a project that was led by my PhD student, Shubo, and what Shubo did here, the first thing he did was to investigate the recrystallization behavior of 316L produced by LPBF. And so he went on and produced a bunch of different compression specimens using another 3D printer at NTU, another set of process parameters, The one thing that I think is interesting to note here is the heat treatment, which is 1050 degrees C for 30 minutes. It's pretty standard heat treatment. And that's what we'll use throughout the second part of my presentation. I won't mention that everything you'll see is heat treated, but it is. And then he compressed all these samples to a different extent, a different degree of strain. This is microscopically measured, of course. And then milled them, heat treated them, cut them up, and used EBSD to study the recrystallization behavior. And so all the results are here. It's a rather busy chart, so I'll walk you through it. X-axis, you see mechanical induced strain, the strain I was talking about before. And then you have two y-axis. One shows the recrystallization fraction, and that would be the black curve here. That's the one that I want to draw your attention to. This is the one that is more important for this topic. The other axis shows the twin boundary, the grain boundary character fraction. So we're looking at red curve, these are twin boundaries, and blue curve, these are low angle grain boundaries. The take-home message there is that there's an anti-correlation between the two. And that twin boundary fraction follows closely the trend, the recrystallization trend. Now, maybe not so surprisingly, what you see here is that there is an inflection point. Above that level of strain, most of the material undergoes recrystallization. That's also what qualitatively you can see here from this EBSD map. Below that, what I call a mechanical kick, below that level, basically everything is stable. Most of the microstructure is stable and doesn't undergo recrystallization. And so here Schubo started to ask himself, well, if I want to be able to drive recrystallization site specifically, it's absolutely impractical to consolidate a layer and then flat punch the layer where I want the material to undergo recrystallization. So I have to figure out a way to get rid of this mechanical kick, or at least bring it down such that it's not going to disrupt my AAM process excessively. And the first thing that comes to mind is that, well, recrystallization is driven by strain energy, and I can maybe engineer the strain energy that I have, the residual strain that I have in my microstructures through or by playing with the laser parameters, because we all know that AAM gives us non-equilibrium microstructures. And so the first thing that Schubo looked at was to change the laser scan speed. The rationale here is, if you go fast, you're probably also increasing the solidification rate of the alloy, and you're also increasing the cooling rate. And high cooling rate corresponds to high GND density, and GND is basically the textbook driving force for recrystallization. And so he did another set, actually two other sets of samples. All these results were at 600 mm per second, which is the data point you see here. He also added 800 and 400 mm per second. Then he introduced the mechanical kick in all of them, and then studied the recrystallization behavior. Surprisingly, what he found was that if we go fast, we actually have less recrystallization than before. This is, somewhat close to maybe 30% of the volume. However, if we go slow, at 8% strain, we basically have complete recrystallization. So that was very counterintuitive, because it was opposite to our expectations when it comes to GND density driving force. In fact, we checked the GND density and found that our initial hypothesis was sort of true, sort of correct. Go faster, you have slightly higher GND density compared to the other two microstructures. And so after digging around, we realized that the controlling feature for recrystallization, for the thermal stability of stainless steel 316L, is what I told you at the very beginning, which is the microsegregation throughout the melt pool. Right? So here you see two TEM micrographs from the 400 mm per second and the 800 mm per second microstructures. We did EDS on those, and you can see that when we go fast, we have significantly higher solute concentration at cell boundaries. And solute here is molybdenum, chromium, stainless steel 316L. When we go slow, we have a much more homogeneous composition throughout the material. Not only the amount of solute, or the solute content in cell boundaries, is higher when we go fast, we also have many more cell bandwidths per unit volume, excuse me, which actually reinforces the idea that the cooling rate here was higher, right? So the conclusion here was that the stronger this solidification structure, what I call stronger is basically a high amount of solid segregating at cell boundaries and also a higher density of cells or cell boundaries. The higher is the alloy's thermal stability, so the more difficult it is to trigger recrystallization. Which means that if you find ways or strategies to weaken the solidification structure, site-specifically this time, you might be able to trigger these differences in recrystallization behavior, which is exactly what we did here. So here we didn't make a new QR code. Instead, we wrote AGBE, which stands for Additive Grain Boundary Engineering. If you're intrigued by that, you can maybe read a little bit more about it in this perspective article we published earlier this year. The idea would be, can we benefit from grain boundary engineering, traditional grain boundary engineering, but also in additive manufacturing processes? I will not have a long detour on that for now. But this is again stainless steel 316L. You're looking down the build direction. This is Inconel. It's a 7-5 Inconel. This cross section, which is a cylindrical cross section, you're looking down the build direction. And this cross section here, the build direction is vertical, and you see lamella with different thickness and different periodicity. That was to test the spatial resolution of this technique, of this strategy, which is in the ballpark of 100 microns, I would say. Right. So that brings me already to the conclusions of my talk. Here I just want to reiterate what I told you at the beginning. So the idea is that if we figure out intelligent ways to control the melt pool and solidification of the alloy at the melt pool level, for instance, melt pool geometry and microsegregation, which are the two things that I showed you today, we might be able to have additional knobs to control the microstructure of the materials that we make by AM. And I think that's, at least to me, that's an extremely exciting new paradigm when it comes to alloy design, keeping composition sort of constant, but changing properties by engineering the microstructure and combining different microstructures together. Yesterday we heard a great talk from Christian Langenbach's group showing how to leverage that kind of approach to improve the overall performance of shape memory alloys. So that's very much in line to what I'm telling you here. Again, clearly this was a processing talk. I showed you processing strategies. I haven't mentioned mechanical properties, corrosion properties, or anything like that. That's because it's all unpublished and we're still working on it. But hopefully AAMS 2023, I'll be able to share a little bit more about that, so stay tuned if you're interested. I'll leave you with, well, first of all, I want to thank the funding agency for this work, which is the National Research Foundation of Singapore and my previous university. And to you, this is my new email contact information if you want to reach out and talk about these strategies and how they might help your design of structural alloys. And this is the last picture I took of my group after a big party. You can probably tell that the alcohol content in this figure was relatively high, somewhat like yesterday, I think. Yeah, so that was a lot of fun. Well, anyway, I'm done. Thank you for listening. I'm happy to take questions.